Hey guys, this is beginning of chapter 2 in physics. We're going to start covering, describing kinematic motion in one dimension. We're going to start with just one dimension, which means, if we think about it, just horizontally across the page. Technically, something could fall vertically and that be our one dimension, and that's something we'll discuss. But for right now, we're going to start just thinking about it horizontally in one direction. We might come across some problems where we look at it differently. But we start talking about the motion of objects. People have searched and tried to understand how to describe and how to model objects as they move for centuries. And what we're going to focus on to start is we're going to talk about, again, that straight line motion. So things like rotation, any twisting or bending, those things are going to be ignored. Typically, we consider this what we call translational. It translates across the page, translates across the floor. So it's one direction, funny joke, if you laugh, good for you. And we're going to think of it as an object moving from side to side. We understand there are more things involved than just, hey, the object is moving across the page. But we're going to start simple. That's just the way we should always start. Start simple and build our way up to the more complex. And so one of the first things we have to understand is what we call reference frames or frames of reference. We need to understand that when we talk about an object moving, that we have to come to an agreement on what not moving is. This picture that they have right here, we'll look at real quick, just kind of identifying some key ideas here. If I'm standing on the side of the train tracks, watching this train go by, and let's say the train is going 30 meters per second as it goes down the track. Let's say this person is walking 1 meter per second. If I were to try and time or speed or radar gun that person walking, if I'm standing still on the outside of the train, I would say that the person is traveling 31 meters per second. However, if I'm on the train and I'm referencing that person, I would say that person's only traveling 1 meter per second. So we have to come to an agreement on every problem. What do we consider zero or motionless? And then we measure everything relative to that frame of reference. Coincidentally, we also have some flexibility in terms of direction. Traditionally, we would say that up and down is our y-axis, positive and negative, and that right and left would be our positive and negative x-axis. But there's no reason that we have to follow that. What I consider up here in America might be very different than what up is in Australia in terms of the global view. So we often have to set an axis, an x and y axis, in order to actually have a frame of reference and a direction that makes sense. So those are just a couple of things we have to kind of keep in mind. Now there are a couple of things that we have to look at in terms of how we measure and make calculations. We have to understand that there are words that we're going to use that are very distinct and very specific. And so that have a specific meaning behind them. We're going to split most measurements that we take into two categories. Okay? Category 1 is what we call a scalar. Okay? S-C-A-L-A-R. The other type is what we call a vector. V-E-C-T-O-R. And as we classify these two different things, we need to understand the distinction between them. And that will help us understand why they're measured differently. A scalar value is what we call magnitude only. So you can think about it in terms of size. Okay? You'll understand it a little bit more when I talk about the difference over here with a vector. A vector is going to have magnitude and direction. Now, if you've watched Despicable Me, that should make you laugh a little bit. Direction. Okay, so we have magnitude and direction here. So it's not just size, but it's also which way are we going, or which way is it moving. So an example of scalar versus vector, okay, would be the most basic one. Is what we call distance versus displacement. Okay, so what we mean by that, when we talk about distance, we talk about how far did you travel. Think of your odometer on your car. You drive 10 miles, it says 10. Displacement is the difference between where you started and where you ended. Specifically, it is what we call x2 minus x1. Position 2 minus position 1. And so it's entirely possible to have a distance that's large, but a displacement that's not. Let me give you a classic example. The most common one that I can think of that everybody should understand is running around a track. When you run around a track, one lap around is 400 meters. All right, sorry about that. I had to step away, and we're back at it. Okay, so we've got distance versus displacement. Displacement meaning, okay, so back to the track analogy. There we go. If I ran one lap around the track, I would say that I ran 400 meters. That's the distance I've traveled. However, if we were to actually measure my displacement, which is ending position minus beginning position, the displacement would actually be 0. Because half the time I'm running this way, half the time I'm running this way, those vectors would cancel each other out in terms of displacement. The direction matters. Okay? So this concept of vector versus scalar is a big deal. And in our world of physics, we're going to do a ton with vectors and displacement. Okay? If we keep going along this line, keep thinking about it. Okay, if we think about it here, we can say that the distance versus displacement is scalar versus vector. Let's go a step further. One that you'll probably really understand is speed. When you look at the speedometer on your car, you're going 25 miles an hour, great, but that doesn't tell you which direction you're headed. If we want to include both the direction and the speed, we get what's called velocity. Okay? And velocity is how fast are you going? Is it positive? Is it negative? Is it forward? Is it back? We can use directions like east and north and south. We can use directions on a compass, like so many degrees north of east, things along those lines. But velocity is not just speed. It's also got direction to it. So negativity applies, just like it would with displacement, where speed is just always going to come out positive. Okay? One last vector that we really need to talk about today is the idea of acceleration. Okay? We will talk about other vectors as this semester goes on, but these are the ones that we're going to talk about today. I'm not going to worry about a magnitude equivalent of acceleration, other than it's an acceleration without direction, which doesn't make sense. And we'll talk about why it doesn't make sense to say acceleration without direction. Acceleration requires or demands that we have some direction and application there. Let's take a look at some of the other definitions that we need to talk about and how we define these quantities. So we know displacement versus distance. It's how far you've traveled in comparison to where you started. Then we're going to get into these ideas of speed versus velocity and how do we actually calculate velocity or speed. So right here we have that average speed, which is what you're used to calculating, is the distance traveled divided by time elapsed. Okay? If you think of average speed as a rate, distance traveled would be like a d and time would be a t. This is a breakdown of the formula you should have learned back in physical science back in freshman year. Distance equals rate times time. It's been rewritten in terms of the velocity or speed, but this is essentially the same formula. We will use this occasionally. This is sort of our speed formula. But I actually like to use the more formal velocity formula. And as we talk about the average velocity formula, we understand that you could technically apply it to the speed formula as well, just ignore the direction, okay? And so when we talk about average velocity, we're going to put a bar over the top to stand for average. Average velocity is defined as displacement or change in position divided by time elapsed or change in time. This is the formula that we use for average velocity. How far did you travel, displacement-wise, divided by how long were you moving. And this is our formal average velocity formula. The acceleration formula is very similar. Acceleration by its definition for average, is any change in velocity divided by the change in time. What this means for us is that when we have a change in velocity, okay, it could be that we're speeding up or slowing down. Later on, we're also going to learn that also includes a change in direction. So if I turn a corner, I am accelerating, even if my speed stays the same. We're going to get into that as we get into two-dimensional motion. Initially, we'll say it's forward acceleration, or we can have a negative acceleration, sometimes referred to as a deceleration. So we have this idea of speeding up and slowing down is our acceleration, and then a constant speed will be our velocity. Okay? So we have those two different things. Our velocity can change, and that implies that there was some sort of acceleration. Now these are average values. There is such a thing as instantaneous velocity or instantaneous acceleration. And the reality is it might take me 3 seconds to calculate, to gather information for a first and a final position to then be able to calculate the velocity. I might want to know how fast is it, not average, but at this exact moment. If I'm thinking about a baseball being pitched, I want to know how fast is it moving while it crosses the plate. If I'm talking about a police car, I don't want to know your average velocity between 2 points. If I'm going to give you a speeding ticket, I want to know how fast are you moving now. And I want to be able to make that calculation. And so instantaneous, okay, this is the algebra equivalent, our averages. If we want instantaneous, okay, instantaneous velocity, we end up having to do a limit. And same thing with acceleration. We have to do a limit. Now, a good chunk of you don't know what that means. Those of you who do know what it means, understand that that is a calculus approach. When we get into the world of calculus in physics, in this class, we take a step back. We reference it, we talk about the fact that for exact answers and precision, we're going to have to use calculus. But we can also have a conceptual understanding that we're going to study in this class to help set the groundwork for us to study deeper in college or university. So understand that we're going to do the basic mathematical approach, but the work of Newton and Leibniz, who worked so hard on developing calculus in order to get at the heart of this instantaneous information, that work is still relevant and very important. Hopefully this gives you an idea of what we're talking about when we talk about scalar versus vector, and also what is average velocity, what is average acceleration, and how do you calculate those. All right, guys, good luck. We'll see you in class. Thanks, guys.